Awesome. Hi, everybody. Okay, so today, Manoj, do you want to come up here? So today we're going to talk about the new unified backend in vLLM that we launched a week and a half ago that supports JAX and Pytorch natively. So first, we're going to go over a very quick TPU overview of what TPUs are, why you should care. Then we're going to talk about vLLM TPU and what the goal of vLLM TPU is and how that's aligned with vLLM upstream. And I'm assuming that folks who are attending this are a little familiar with vLLM because it's the vLLM track. So we'll talk about why TPUs should be in your arsenal. Then Manoj will cover how it works and advanced topics that we think about when we're trying to solve some of the technical challenges that we're trying to solve for. And then I'll go over what's next, what's our main focus for the next 3 months, and to really round out the end of the year. Okay, so TPU inference, or inference in general for large language models. So as you all probably know, models are getting much, much larger. They have to generate significantly more tokens. There's also more stringent SLOs that are being put in place on end users where ultra low latency is becoming much more critical. And then we're also even complicating things even more by adding reinforcement learning where you have to do training and inference as a part of one cohesive loop. And so these are all really hard problems to solve. And Google has a custom-built chip and has been developing it over the last 10 years, iterating on it almost every single year since 2015. And TPUs are really special because they have specialized hardware components that solve for problems that are really unique to AI workloads in general. So they have hardware components like MXUs that provide significant speed up on massive matrix multiplication. They also have something called ICI interconnect, where it's specialized networking that connects chips or TPU chips within a pod, and those pods can be sized up all the way to 9,000 chips using this really specialized interconnect or fast interconnect. And so we iterate on this every single year. And so the problems that we just talked about, TPUs are really great for both training and inference workloads. They're also used internally at Google for things like Gemini, for training Gemini or serving Gemini. But importantly, a lot of cloud customers across many different industries, from financial services to some of the biggest AI labs in the world, use TPUs as their cornerstone chip. So enter vLLM. So one of the big things that Google tries to do is we're trying to make TPUs really accessible and easy to use for a number of folks. Across our customer base, but also just trying to grow TPU adoption in general. And vLLM is a really important catalyst for this. And so vLLM, for those of you who don't know, vLLM is an open source inference engine that its primary goal is to build the fastest and easiest to use open source LLM inference and serving engine. vLLM has an amazing community flywheel. And when we think of those two things that it does really well, so it makes it really, really easy to achieve really high performance out of the box with only a few lines of code. This makes it really attractive across 3 different verticals. So the first one being model creators or foundation model builders end up seeing vLLM as a really important distribution channel. And so some of the SOTA models, when they get released, when they get launched, they're available on vLLM because there's an amazing team in the community that basically lands these models on day 0. The second that's really unique and awesome is hardware interoperability and the hardware diversity of vLLM. And so you have the top layer, which is shared. The interface is shared across anyone using vLLM, so you'll have the same APIs for the most part. But then you have access to different hardware accelerators under the hood. And so you retain that same experience that made it really, really easy to get started. But you can now suddenly get access to a much larger pool of hardware. And then because of all these factors, you have an amazing contribution trajectory of vLLM, where in the last 6 or 7 months, you've just seen whether you're a hobbyist, an academic, or you're working in industry, vLLM is a place where many folks in the community can kind of congregate and learn. So how do we marry these two things? So vLLM TPU shares a lot of the same principles as vLLM upstream to make it really easy and accessible to serve large language models at scale as performantly as possible. And so what TPU does, or what vLLM TPU does, is that we try to bring the competitive cost performance of TPUs to vLLM. And we do this because we want to improve obtainability of both TPUs and GPUs or any accelerator that you have. Google Cloud, we really just want you to have full access to our portfolio and that you can pick and choose which hardware accelerator is best for your workloads. And so rather than fully indexing on one over the other, I think the beauty of vLLM is that you can basically move pretty freely from one to the other. And so this kind of touches on the near zero developer friction. And so by deeply integrating into vLLM or building the TPU backend in vLLM, we retain a lot of the same interface that people have grown to love. And you can retain that. Yeah, you don't have to change the user experience. You can still download the same models off of Hugging Face and run them on TPU really performantly. And then the fourth point is minimal workload disruption. So by adopting the same production telemetry that vLLM has, it's hardware agnostic, right? So you can basically plug and play into different production workloads, whether you're using Prometheus metrics in vLLM for TPU or GPU, they're the same. And so that's really awesome, and it makes it really easy for people to use. Okay, so what did we add, or what did we do? So a week and a half ago, we launched this new high performance backend for TPU in vLLM. And TPU has gone through an interesting evolution in vLLM over the last year. And so what started out in February, so we have April here, but in February, there was a prototype of TPU that had landed in vLLM. And this was one of the first accelerators that landed in vLLM. Now we have a lot more hardware backends, but at the time, it was a very, very novel idea. And it wasn't very performant, but it was awesome. Because it solved a lot of the adoption issue or the usability issue that we were encountering with customers where portability was really, really hard, having to rewrite your model or whatnot. And so as Google, we thought that this was amazing and we wanted to invest more into it. And we wanted to make it really, really performant. And so in April, there were a lot of things that we had in the previous backend that we loved. And so I mentioned this extensively earlier, but user level APIs, native model compatibility, we did not want a user to write a single line of code differently. We wanted you to be able to write the model or run the model definition from upstream in vLLM and just run that directly on a TPU without having to write a single line of code. We also wanted to retain the hardware agnostic telemetry because it just made it really portable and easy. And then the base scheduler, we also wanted to keep that as the same because that doesn't actually have to run on an accelerator that's just written in Python, and it's awesome, and we want to share most of the features with vLLM. We want to stay true to that. But other than that, we changed everything else. So we completely redefined the XLA lowering path. XLA is the compiler for TPUs. We rewrote the runner, the worker. We totally improved the kernels, the foundational kernels like ragged page attention in vLLM. And we adopted a hardware plugin design so that we could move faster and iterate on TPUs without having to, have to merge code upstream all the time, especially if it was just TPU specific. And so we also added JAX and Pytorch support in vLLM. And so a few highlights. So I just said this, but now, today, with TPU inference, the new repo that we launched a week and a half ago, you can run Pytorch models and JAX models natively on TPU directly from Hugging Face. You can bring your own, or you can basically adopt the same flow that you had before. We completely redesigned the ragged page attention kernel, which Manoj is going to go over soon. It's significantly more flexible and performant than the previous ragged page attention kernel. And then we also adopted SPMD, so single program multi-data programming paradigm was adopted as a first-class citizen for TPUs in vLLM. So this is very different than the MPMD approach that GPUs typically use. And so this we did because it just drives significantly better performance. And so from February, when we had this prototype for TPU, to today, we have a 5x improvement on baseline performance, which is we're really, really happy about this. And we want to continue to kind of improve that over time, and we want to increase the complexity of the workloads that we're working towards. So just to really emphasize this, I have the Llama 8B and 70B model because at the time, back then, in February and April, these were like the only two models we could actually run because we were just racing to land the most performant implementation as possible. And so what isn't captured here is that there are many, many more models that we can now run as performantly as we see here. But because we only have the baseline, that is Llama 8B and 70B, this is what we can kind of compare. And so we've seen almost like a 3 to 4x improvement in performance across some of these core workloads. So we're really happy about that. So let's dive into how it works. I'll pass it over to Manoj now, who can go over it in detail.
Okay, thank you, Brittany. Hey, everyone. I'll go over the design of the vLLM TPU. I don't want to bore with gory details, but at least I want to share the mental model of like how we approach the problem and how we design the solution, inference solution on TPUs. So, as Brittany was saying, our goal is to provide an inference solution on TPUs for both Pytorch and JAX models, right? Not different solution, possibly a unified solution. So, which means the key thing is we have three core principles, and and the first one is usability, right? Because especially when you're programming solutions on accelerators or even multiple accelerators, I think usability is the key. You want to make sure it is fungible across different accelerators. GPU, TPU, fungibility is important. Zero onboarding cost. It should be easy to deploy, easy to debug, and it should support many models, right? Like optimally. And the second core principle is like we want to embrace the full OSS ecosystem, and rather than developing an own inference solution for the TPUs, like, okay, let's embrace the OSS ecosystems, look at what is available there, and port it to TPUs. So it's also a less friction point, right? Like when you're especially coming to TPUs. So we want to that's why we fully embrace the vLLM ecosystem, and of course the JAX and Pytorch ecosystem. And the last one, which is the most important one, it has to be the perfect dollar should be better. If it is not cost efficient, it's a moot point, right? Like why would you want to even consider TPUs? So given these three core principles, that's how we started with our design. So we didn't fork the code. We thought like we'll take a hardware plug-in based approach, right? Okay, let's look at how vLLM is designed for GPUs. Okay, so what are the hardware pieces? Like maintain the same abstractions, inherited the same classes, and extended the corresponding hardware functionalities that is needed. Like in this case, like say GPU, TPU worker, TPU model runner, and underneath provided XLA functionalities with Pallas extensions, right? So this is like a more quick high-level overview, right? Like here's a detailed picture, and this is my favorite picture. And like if I want you to remember this one picture for the day, it is this one. I think left side you're all familiar with the current vLLM-based approach, right? Just you have a Hugging Face checkpoint, vLLM model. It runs in the GPU worker in the background, right? Now, moving to the right side, we want to keep the same front-end interface, no changes there, right? And it should support both Pytorch models and JAX models, right? Same interface, should support two frameworks. So we extended that. Now, should we have two different backends to support Pytorch and JAX, or should we have one backend? So to keep our implementation simple, we went with unified backend for both Pytorch and JAX models. So essentially what we did was that we took the Pytorch model, lowered into JAX model. Essentially, we use this library TorchX. It's also open source. You can play with it. It's basically a Pytorch JAX interoperable layer. It just like takes Pytorch tensors, convert into JAX arrays, Pytorch operators, JAX operators, lower the model into JAX model. And once the model is in JAX, I think this this has been optimized well for TPUs over several years. So we were able to optimize using the unified JAX backend. So for both Pytorch and JAX, we use the JAX backend to run the models to get the optimal performance. So that's a key message that I want to share in this picture. So as you know, inference is all about performance, right? If you want to get the best performance, you need to code close to the hardware, right? Whether that's it's in CUDA, Triton, or in this case, for TPU, we have Pallas kernels. Like you write Pallas is a library, Triton-like, to write more high-performance kernels that is close to the hardware, right? Yes, essentially you can, originally people you write your code in JAX and it gets compiled into it. Yes, it was working fine. Compilers are also evolving, but the models are evolving even faster, right? It works well for dense models, right? But for most demanding workloads or like sparse models, ragged tensors, it's relatively hard. So you need to probably, if you want to get the highest performance, you have to go a layer below to write more high performance kernels. So we have written few kernels to get the best performance for our dense and sparse models. So Pallas is a low-level Python-based APIs. This gives control over how do you want to tile your computations, like schedule your communications, schedule your data transfers, the whole 9 yards on how to program the hardware. So I'm not going to talk about all the kernels. At least want to talk about a couple of them. Brittany mentioned briefly about RAG page retention. This is the V3 version of our current implementation. Like when compared to V1, this is like 5x faster, and the performance keeps improving, right? So this is a very general purpose kernel. This is not written for a particular model. This is a general purpose kernel, and we have an auto tuner that tunes for different models. Naturally to get the best performance. It has much more deployment flexibility. We didn't have that flexibility in the V2 kernels. Like for example, the head dimension is fixed, so it's not naturally applicable. So this one is much more programmable, and with that flexibility, we even got a 10% performance improvement. So, but we keep continuing improving the page retention. The next kernel, which is also sort of like a mega kernel, especially if you're running MOE models, MOE part takes majority of the computation time, right? Or majority of the overall time, right? Like in some cases, like 80-90% of your time is part of the MOE, right? So we wrote one mega kernel, fused kernel for MOE. It's aggressively pipelines. The key goal here is to overlap as much communication as possible. In fact, we try to fully overlap the communication over the SWG FFN computation, like GMMs. I'm not going to go into the details, but that itself is like a separate session talk of like it's easily half an hour, 1 hour talk to talk about to go deeper into like how this kernel is implemented. But I'm happy to if anybody wants to talk about it, I'm happy to chat offline about that. So with that, like, okay, what's coming next? Like, what is keeping us busy, right? Like, what are some of the challenges ahead? Like, what is keeping us busy? What are our current focus in the next quarter? Brittany will cover that. Thanks.
Thanks, Manoj. Okay, everybody's we got to bring the energy up a little bit, I think, right? Okay, I don't know if we will. We already saw this slide, so as you know, I just want to revisit 10 years software, hardware, co-design. The biggest thing that what's next is Ironwood is our next TPU chip that's being rolled out now in private preview, and then public preview is starting late November, and then December is like the big GA announcement. And so why is Ironwood really special? So how many folks here have actually used TPUs before? Yeah, okay. Okay, cool. So Ironwood is by far the largest chip that we've ever announced in terms of scale out across a single pod with that ICI interconnect that I was talking about, but also just like HBM available per chip is also significantly higher than any chip that we've launched. And so compared to its predecessor, it has 4.5 times the HBM memory bandwidth than before. It has 6 times more HBM capacity per chip, and it has 2.5 times more T-flops. Our previous pod size was 256 chips, and so Ironwood is 9,216 chips using this networking. So very, very massive scale. When we think of the previous generation TPU chip, like Trillium, it has really high T-flops and not so high HBM bandwidth when compared to Ironwood. This is great. Like if you have compute-bound workloads like prefill heavy workloads or multimodal model implementations that you're serving that are typically more compute-bound, Trillium is, and maybe smaller models, Trillium is an amazing chip for that. It is, I say, the cheapest perf per dollar or cheapest flops on the market by far. So small models, prefill heavy or compute bound, and then latency sensitive because of the HBM memory bandwidth being a little bit lower. Ultra low latency is just not typically seen on the Trillium side, as opposed to Ironwood, which is a very, very large chip. This unlocks many use cases that Manoj had kind of talked about, so alluding to what are the things that we're really working on and what we're really focused on. So Ironwood is coming. It's a much larger chip, and it unlocks XL scale MOEs for us in terms of just sheer specs and like what we can get from the machines without having to go necessarily to multi-host. Although multi-host is totally fine, it's just it's always nice to not have to do it if you don't have to. And so reasoning models, when you think of hero workloads for Ironwood and vLLM TPU in the future or in the next couple months, think large-scale MOEs, generating massive amounts of tokens. That's where you're going to really see the best bang for your buck with Ironwood. And of course, ultra-low latency. So the use cases that we're thinking about, so offline inference is obviously like the vanilla use case that everybody has to solve for. So I can't have a slide like this unless I mention offline inference. The second point is ultra-low latency. So like I said with Ironwood, we have to start thinking of different design principles of how we actually can achieve more aggressive SLOs for our customers. And then the third is reinforcement learning is a really important use case for us over the next 3 to 4 months, both for JAX and Pytorch models. So LMD integration, I know Rob Shaw had a session here, I think earlier or maybe later. LMD is an open source framework that uses a bunch of composable parts out in open source to make up a really high performance production inference stack. And so vLLM is the backbone of LMD in terms of inference engine, but it uses things or borrows things like from LM Cache, from Inference Gateway, also led by Google in partnership with Red Hat. And it consolidates all these different composable parts and makes really high performance production serving accessible to folks in open source. And so things like disaggregated serving becomes much easier. Prefix-aware cache, prefix-aware routing also becomes something that's accessible, which wasn't really the case previously. So LMD integration in terms of just supporting more complex deployment patterns is a big focus of ours. The next is, as I mentioned, distributed RL integration. And so, like I said, or Manoj also mentioned as well, we support JAX as the lowering path, but we also support Pytorch models as well. And so really building out more advanced capabilities for distributed RL integration is a big focus of ours in the next 3 or 4 months. Things like weight sync, even thinking about like heterogeneous deployments across, like when your trainer is Pytorch or your sampler is JAX, like mixing and matching, not being so locked into whatever your RL lab is doing or your research lab is doing, for instance. Trying to kind of blend or find opportunities to blend these design decisions a little bit more is really our primary focus. If you're interested in trying TPUs, please join us on GitHub. Everything is open source since we launched a week and a half ago. You can, of course, go to the main project upstream, but if you want to start using TPUs or are curious about TPUs, please visit the TPU inference repo within the vLLM project, and you'll find the Slack channel. You can get involved. We have a bunch of first issues that we recommend for first-time users too. Thanks very much.
All right, we have some time for questions. Do you have any questions from the audience? Will these TPUs be available outside of Google Cloud?
Yes. Yeah. So the TRC program is one of our one of the most awesome. If you're affiliated to academia at all, we actually provide free TPUs. Many free TPUs have been issued to folks at academic institutions across around the world, basically. So definitely, if you're affiliated to research in any way, I would definitely check out the TPU research credits that we issue. And then otherwise, Google Colab also supports TPUs as well. And so we saw folks were running, with the new announcement or the launch that we made a week and a half ago, you can now run vLLM on almost any TPU generation that is now functional, which is great. So give it a try. You can try it in Google Colab as well.
Thank you very much for a very interesting talk. Two questions. One is, are TPUs ever going to be available outside the data center, especially as they have now these low latency capabilities that could be really useful at the edge? And my other question is about the XL MOE kernels. Super interesting. How do you get the all-to-all expert communication working without significant hits to efficiency?
Do you want to take the kernel one first?
Is this one?
Or I can also take the other one too.
What was the first question?
No. I'll take the first
first,
one.
okay,
I can
yeah.
take the first question. Okay. We didn't coordinate that well.
And the second question is all-to-all overlap?
All-to-all communication between experts.
Mm-hmm.
And how do you manage? Because obviously, when we with sparse activation, a lot of the benefit is the efficiency gain that we get. I can understand using more compute, but do you see some performance deterioration with that kind of a kernel architecture?
So a couple of things. So we chose our tiling and block sizes based on that. And second thing is the all-to-all communication itself. We just rewrote from scratch just for this kernel purpose.
Yeah,
so,
awesome.
yeah, I can talk to you more about that.
And then for the first one, not today, but we don't know what the future holds. But today, there's nothing outside of Google Cloud or the two different paths that I mentioned previously.
I was going to ask a similar question, basically, can I buy a TPU and use it locally? Because typically your development workflow is you have a local laptop or a development machine that you develop code. It works on CUDA. Okay, I deploy this online. It works on the web server, on a cloud platform is fine. But lack of this local setup, you talk about low latency, right? If you don't run locally, there's no low latency, right? And another thing is, for example, for people who work on robotics and simulation, having this working on the cloud is just not the solution because you need something that works on embodiment and it has to happen locally. NVIDIA, for example, has a full lineup of robotic applications and also serving online. So basically, you can use the online-offline integration to do a lot of more things. But if you choose to use TPU, then your only solution is online, right? Then simply based on this, I think this rule out a lot of customers, especially in the physical intelligence world. Yeah.
I can't, it's not built for every single use case, which I think is why if I were to talk about the importance of vLLM for this, and this kind of goes back to the story that I mentioned ahead of time, I can't speak to the future of what our adoption will look like or what different user journeys, I guess, we will support in the next year or so. But what I can say is that I think that's why software like vLLM is so important, because you don't have to over-index on one like you used to. I think portability across hardware is really important for that exact reason, so that the toil of basically moving from one to the other is not experienced in the same way, because it's just providing more optionality, so that when you can use it in cloud, you have access to the best per dollar that you can. I'm actually not. I would imagine yes. But I don't know. I'm not affiliated with that lab. I'm sorry. We could probably put you in contact with some folks, though. Yeah.
How big are these TPUs? I'm just wondering.
I was going to add a picture. The chips themselves are like this big.
Okay.
It's the racks that end up being cooling, and it's all the other stuff that ends up being really.
Yeah.
Thanks for sharing all the details. I was curious to learn more about the auto tuning part that you mentioned on the generic kernel that you built. So are there specific parameters that you tune, and is the tuning just at the beginning of the model launch, or is that something that you have to do before the model launch, or something on those front?
Yeah, I can take it from here. Oh. Thanks. So yeah, like for the model launches, yes. For example, this has to be tuned for that model, and if a new model is being launched, yes, we need to tune the kernels to get the best performance for that new model architecture or for the new model parameters. Yes. Yep. For the single model, right?
It's actually shapes.
Yeah.
It's like shapes based.
Yeah.
Yeah. We have it's not different than GPUs in that way. Like kernel tables, like lookup, block sizes and stuff, you still have that for TPUs or for GPUs as well, for the most part, from my understanding, and so it shouldn't be that different. But yeah, if you want the best, there's a difference, right? Like you can have really good performance out of the box, and you can have peak performance out of the box. And so, like what Manoj just said, in order to get peak performance, tuning is required, but it's not necessary.
I'm sorry, we have to. We've been asked to empty the room. So yeah, thank you so much to Manoj and Brittany for your great presentation.